the starting point was February when the Internet Collaboration announced the highest energy event ever recorded in human history. So about 200 PV neutrino impeding in the Earth, which started even violating causality conversation on whether or not the internet is in tension with ice cube, not having observed anything in the similarities. This, you know, this led us to sort of start from scratch and think about internet telescopes in general. And as I will tell you, try to propose a first principle formalism for making a prediction of appearance. And so the starting point that I would like to make is that, in some sense, just not this sense to get me. Sorry, there's a typo. In some sense, neutrino telescopes are like huge fixed target experiments. So neutrino arrives, there it functions as a slab of material in which it can convert to stuff, mostly ions for what we're interested in. And then you measure in the detector something out of it, which we'll discuss. And it can be used for a variety of targets. For example, mostly to measure the flux of neutrinos or any other particle reading, under some or even infer properties of neutrino interactions, the Earth density profile, and whatnot. For example, the Internet event is sort of probed the kinematic region that was still untested by traditional experiments. So the deep inertia scattering interaction of neutrinos in untested kinematic areas. It can also, for example, be used for indirect detection of dark matter. If the dark matter in the case, neutrinos or has neutrinos in the there are several types of events that can be registered at neutrino telescopes. They can broadly be divided into these two classes. So cascade-like events, like on the right, which are mostly initiated by neutral current interactions of neutrinos within the detector, which release a large amount of energy, mostly in the form of hadrons which don't travel long distances. So they have this sort of blob shape. The PMTs that light up from this sort of blob shape, or which are the ones which you consider, they can be mostly muonic tracks. So muon you produce inside the detector, outside it, travel through it, and release energy as it travels. So it shows a track inside it. This is a type of event that, for example, the Internet event, sort of topology that event. So if one considers only muon tracks, in some sense, neutrino telescopes are actually muon telescopes. And as I said earlier, our aim was to construct the first principle formalism to the computation of the rate of muon tracks inside the detector. In particular, we thought of employing the formalism of transport equations or Boltzmann equations. So defining a phase space density of muons, which evolves according to some transport equations, and thanks to which one can compute a number of observables, including the rate of orbital. So this is not a completely new approach, but so there are some examples in literature that have this with Boltzmann equations, but somewhat they was not brought till the end, let me say. So from the parameters of neutrino flux directly to the experimental rate, only using the forward. So this is a graphic representation of the system of Boltzmann equations, sort of a simplified it from once. System of Boltzmann equations. So one such that the only thing that is unknown, something at least, which is the neutrino plot at the Earth's cross. These neutrino flux will have both a muonic and a tau component, as well as an electron component, of course, which doesn't end in this however. So muonic neutrinos can then, interacting with the medium, they can upscatter to a muon, which then travels toward the detector or is produced directly inside the detector, and it eventually detected. Tau neutrinos, on the other hand, they upscatter to cows, of course. Here, the situation is lots more involved because tau travel for finite distances, which and then they decay to either muons, so to muons and neutrinos, particular to muons, which that travel at part of that. But of course, the tau decay can repopulate, for example, neutrinos in this process. So in principle, the system of a Boltzmann equation is really complicated. But under some assumptions and sorry. So under some assumptions such as neglecting societal repopulation and sorry, I got distracted. So under the assumption of neglecting this neutrino repopulation effect, one can solve the neutrino tau system once and for all and feed it into the equation for muons, which takes this the following form. So it's a standard form of Boltzmann equation. So you have so convective derivative on the left and a kernel on the right, and this kernel somewhat encodes so both the upscattering of neutrinos to muons and the decays of taus, or actually whatever new particle decays to muons and is produced by neutrinos, in the form of fully differential cross sections or decay rates that enter through the usual positional term. Right. Now, one of the main assumptions that we made is that some of the processes, namely the QED ones, are they act on much faster timescales with respect to the actual read processes, which are those responsible for the creation of muons and neutrinos and the decay of taus and not. And so they can be effectively included in the rate of energy loss for the muon rather than the full collision of the syllables. Now, here it sort of gets sort of tricky, and maybe I'll talk about this a little later. But so essentially, one can employ very well-known formula for the energy loss of particles, and so the rate of energy loss is just the velocity of the particle. It's always assumed to be also relativistic in the energies of Lagrange times the dx, so the sort of Bethe block formula for the energy loss in while traversing a stab. If one then neglects processes that act on longer time scales, such as muon decay or the repopulation of your neutrinos, one gets this system. So actually, one equation that resolve the other system of differential equations with partial derivatives, as opposed to a integral differential, so a system of differential equation, which is much more complicated. So in principle, one can solve this equation. So in general, at neutrino telescopes, let's say from tens of GeV up to whatever, to 200 PV, it's the highest that are recorded. For the ones that you're interested in, we're talking about hundreds of PV. Yes, sorry, the neutrino energy. Yes. Sorry, I know that your question. Yeah. Of course, a neutrino of a fixed energy will produce in the detector muons of all the energies below it, because, as I will also comment later, neutrinos can convert to muons far away from the detector. The muons will lose a lot of energy and arrive with much smaller energy than the parent neutrino, or they can convert directly in the detector, and essentially the energy of the muon is the same as the energy of the neutrino. Of course, since energy loss is exponential, you cannot produce muons too far away in the detector, otherwise they quickly go below the threshold, so to say. So, I don't know if this answers your questions. So the muon, so the recorded muon energy for the KM event, for example, was about 100 eV with a very large 100% or more. And so, and then from the muon energy, you have to reconstruct the neutrino energy. Wanna talk a little bit about that later, about why you should do that. Yes, I mean even for low energy in these ranges muons, the lifetime of the muon is much longer than the time it takes the muon to cover. So it would be a problem for muons whose energy is much below the pressure gradient. So essentially, muons are a stable part of it. Well, yes, that would complicate the matter a lot because the equation would not be differential. There would be interdifferential because the population of neutrinos depends on the distribution of neurons or cows or whatever. Yes, that's for sure one of to like go. Um, so the approach that we took was one that sort of borrowed from cosmology, okay, namely the line of sight approach, which consists in finding trajectories in space along which the equation is ordinary. And one does so by solving differential equations, ordinary differential equations with a time space and two variables, which give the correct coefficients for the variable computation. So this show you the system of these characteristic trajectories, as one called it. And so we hear this psi, which is the dimension of length. And just they track they track the motion of neutrons from the Earth's cross detector, and time and position are linearly dependent on psi, whereas the neutrino and the muon momentum has an exponential dependence on the length of the path of the spot point. This way, so the equation becomes ordinary. One find the solution by integrating the kernel, evaluating on these appropriate trajectories, which with the boundary term which at this 0. And so the solution somewhat encodes this relation between the neutrino energy and the conversion point. So psi labels the point where the neutrino converts to a muon, which then loses energy and arrives at a certain energy at the detector where it is detected. So fixing the measured muon energy, one gets a relation between the neutrino energy and the point conversion, along which one has to sum. Of course, because of this exponential dependence, the typical range of the integral is sort of gets affected radius, which is of the order of the range, so the length by which one loses its energy. So one per b onward. Forget to stress it before b is a parameter. So which is somewhat larger, but of the order of the okay, so let me go on and actually arrive at the definition of the rate. So the expected rate of muons that term. So the formula has two pieces of that. So the first one, which is the case of muon neutrinos generating muons. So as you can see from this picture, so psi labels the point where the neutrino converts to muon, and then this is summed over. And the kernel includes the Earth density, which needs to have an appropriate profile. One of new models, the picture, the fully differential neutrino nucleus or neutrino neutron, so neutrino target interaction, and an impinging plus of it. So of course, there's also factor that takes into account the attenuation of neutrinos. So as you go deeper and deeper in Earth, the flux of neutrinos is attenuated by the fact that neutrinos convert to muons, so you lose neutrino. In the case of tau-initiated events, is much more involved because the tau neutrino converts to a tau at a point psi prime over which one suns. Then the tau traveled a certain distance, and at a point psi converts to a muon over which you sun. So the kernel includes both the fully differential cross section for the version of an infinite tau, the decay of the tau into a muon, attenuation factor, which actually, so it's written this way, it's the same attenuation as before, and then you have a extra one for tau attenuation, which depends on both psi and psi prime, which includes the fact that it's traveled. So how many taus and u's produced actually depends on both x and x primes. In principle, we're going to get. Okay, so this is somewhat a master formula that allows us to compute the expected rate of mu on the detector, starting only from the neutrino plot that it was. Note that under some approximations, there's no need to blowing Monte Carlo simulations for the predictions. This is at some level of risk. So the next step is to have a case study, and we use the ultra high energy event pre-motivating. Now the main goal, the target, was to assess its energy if relevant indicating a nicely relevant this event. And without going to detail of the statistics, I'm just gonna use this ratio of expected number of events in experiments as somewhat of a proxy of the tension. We consider several cases, both diffuse fluxes and point sources, with several spectra, both power law and energy localized, and also consider the gated transit source. Let me start with the diffuse power law, by which you just mean a flux that does not depend on the angle of the angle by which the neutrino is coming, and we consider power law spectrum, so minus gamma. In this case, the ratio of expected number of events at IceCube versus internet is pretty robustly about 70. So it does not depend very strongly on gamma, other parameters, which translate to about 3 sigma tension in two experiments. This is a plot I really love because it really looks like an X and bane, and also is up to segments. I don't know. In which you can clearly see the tension between the experiments because it used to islands somewhere. And also you can see the degeneracy between this particular internet, in which you only observed one event between the normalization of the flux as a spectral index. Here we can have a larger spectral indices if you compensate the law at all. And yes, thank you. So we're considering only through-going tracks. So since we only focus on sorry, not through-going, track-like. There's a typo. Track-like events at IceCube from 12-year data release. Since we only, so our formulas are up to now and only account for track-like events. So one tracks is the detector from 12 years. So these span from all the energy ranges from 2 TeDs up to hundreds of PeDs. And for the case of internet, there's only one event, which is they commented about the errors. So here it's actually only statistical. We do not include any systematic effects. Well, yes and no. I mean, one of the advantages that I'm gonna comment later of our approach is that you can easily take into account systematics because they're not hard coded into simulations which are attained by their collaboration. And I'm not sure that I have perhaps a backup slide of this. I, I think I do, but these are like in each bin you have a Poisson likelihood, which represents the expected number of events and the measure. Uh, and then the likelihood price cube is just a product of the likelihood bit. Whereas for internet, there's only one bin actually. So somewhat an implicit assumption is even if internet takes data at lower energies, that it does not, it's still compatible with IceCube diffuse fit. So it makes sense to only compare the ultra high energy bin with the diffuse fit mice. No. Yes, of course. Well, yeah, that's true. That's true. That is true. So we take a model and play it for background for mice, which that is true. It does result of statistic in systematic. So yes, that if that's something you have room to play. But high energies, there's no background at all. Because of internet, there's no so very little backup. So that's very good. Um, Let me go on to the case of a point source. By point source, I mean a flux angular dependence is just is sort of fixed in such a way that uh, so that tracks the time evolution of a point in sky, the rotation of Earth. Actually, this was something that we discussed discussed a lot because, as you can see in this plot, along the time of a day, approximately, no, a long time of a day, um, the depth of the detector as seen from the direction of a hypothetical point source that is fixed to be in the right direction of from which the internet event was observed spans several orders of magnitude in the internet, whereas the ice cube, being at south pole, is always approximately at the same time, which is at the core of ideas for resolving the tension, which you can make distances or depths larger than about 100 kilometers special with respect to distances smaller than about 100 kilometers. Yes, special in the sense that they yield your events in such a way that ice cube would not be able to see any events from that kind of physics where I can see a lot. Actually, this is not the case that this is standard, so it's standard of physics. And one arrives at a larger ratio of expected number of events, resulting in a larger tension. And one way to appreciate this is the fact that, of course, with the with the larger depths come higher attenuation of neutrinos. So ice cube does see a more limited portion of the sky at any time. So on average, in a day, it sees a smaller portion of the sky, but with let's see, like better somewhat, meaning that the neutrinos are much less animated, and essentially they're not animated at all, but to the boundary of this story for her. Whereas internet sees a much larger portion of the sky, although with a higher transparency. But actually, the average transparency in a day is about the factor of 2 that one loses considering a point source of this way. So I'm at the conclusion, and here is a table which summarizes the tension between ice cube and internet. The first thing that I want to say in the conclusion is, so the only case in which you can actually gain and solve the tension you can do experiments is the case in which you consider a point source, which is transient, so that only emits through a shorter time span, such a way that ice cube and internet are not that different at all, because ice cube does not take advantage on the 12 years more of exposure inspecting internet. Whereas in all other cases, the tensions are, well, not very large, but like compatible with the compatible with the case of fuse. One important point that in the case of the point source, we find a larger tension than in some other work. To summarize the formalism, instead, let me say that, as I commented before, the advantages are among the advantages of the following. So you directly link the physical parameters, which can be either the neutrino flux parameters or the physics parameters, directly to measure quantities. I mean that you don't need to you don't need to rely on assumptions made by collaborations, either on seminal physics or new physics, or action zero, or the reconstruction of the human energy when you perform phase, for example, to infer physics or parameters, whatever, plus. And on the outlook side, there are several directions along which we can go now. One somewhat easiest thing to do is to extend the formalism to other event topologies, for example, the events. Then, as I told you, there's this sort of tricky point. So the way in which we treated the muon energy loss somewhat assumed the continuous, so a limit in which the energy loss is continuous as opposed to diffusive, which is something that is really subtle and would complicate the solution of the grade B. So we look forward to putting this in the description. Moreover, strictly speaking, the equation we wrote is an approximate Boltzmann equation. It does not insert the number of particles. This because essentially we can stitch a distributed system. So one would need to consider the full Boltzmann equation in order to avoid this problem entirely. Relating to that. Tau-induced events are subtle because of the several scales that intervene in the problem, so they need a dedicated freedom. Sure. And one long-term aspect of this project implementation is following public code which is allowed at past predictions. Thank you for the attention and very. I'm not sure I understand what you mean. No, I would say. So yes. No. I mean, from the master formula you can do it, but then I mean, for the case of that, actually, we only bin it. We bin it in a way that is compatible with energy resolution, but we don't marginalize the distribution of the neuron energy. And this is the question. This is the so it's a bin. I can't remember the details, but it's from about 10 PeV, so the highest above the highest energy that I spit ever observed, up to virtually any sensible upper limit. And this is a way to somewhat take into account the energy resolution of K. So in this sense, yes. So in the way we've been, but not like I'm more specific. So we don't. No. I agree. Indeed, we did not do it, but like it answers the question. Then yes, and there's a question of the resolution of the neutrino energy, which you don't really care about in this formalism because you don't ever need to look at reconstructive region energies. Actually, this would constitute an independent way of reconstructing actually these which is one of the steps. It didn't announce the show. That's I that uh uh impossible. No, no. We've talked about the answer several times. And really concentrated. I'm afraid I won't be able to full answer right now. I apologize. But it's okay. I accept that. Sorry. The yes. Well, I did not show that. So, well, to simplify, so what Andrea is referring to is the fact that these base factors are constructed by assuming, let's say, that the ice cube results are reference model for the results. So you trust ice cube in a sense, and use that as a reference to prepare taking that. So the test. One can in principle do the opposite. In the case of the diffuse, it doesn't really make much sense with the data that we use because ice cube has much more data and so somewhat a consolidated result. The ice cube. But for the case of point source, one can. So since there's one event at high energy that we're not ever probe, one can in principle say, okay, and first to ever observe new source. So one can trust the empty net and construct the answer in this way. Uh, uh, it will be gigantic, for gigantic. Yeah. So as one would maybe that is such as the one you're having with the most in the yes true that is the degradation of the well, unless Cantrand publishes diffuse data which are also intentionally realizable, in which case plus point source. Yeah. Well, with the data that we use, it doesn't really make sense to trust Internet in any case in which you include diffuse. Because the only data with for low energy, sorry, for low energy. So the only low energy data that we have with life. So even if you do diffuse low energy plus point source high energy, it doesn't make any sense to trust internet modernize. I was in time. Thank you.